Hello, children. It's story time with Professor Lanterman. Today we'll be looking at Analog VLSI and Neural Systems by Carver Mead. In particular, we'll be looking at this circuit in figure 11.1 on page 180. So I'm going to draw a little trapezoid here with a plus input and a minus input, and these are voltage inputs. And this trapezoid is going to represent an operational transconductance amplifier, not to be confused with a regular operational amplifier. A regular operational amplifier has a voltage output, but an OTA has a current output. So we're going to suppose that this is operating in the linear region. I'll come back to that point. And it has a transconductance gain of GM1. So it's going to take the voltage inputs, difference them, and multiply that by GM1 and give you the current output. Now, usually we will write this with a third input that indicates a current input that controls the bias current that controls this transconductance gain GM1. Here, I'm not going to explicitly write that. We'll assume that all the circuitry that generates that current is included in this symbol. This is something that a lot of folks who do integrated circuit design will use. So this is feeding a capacitor, C, and I'll have another transconductance amplifier here, and this is going to feed another OTA. So I'll draw a little trapezoid here. And this is the positive input, here's the negative input, and this has a transconductance gain GM2. And this is going to feed another capacitor. Now, I'll assume the capacitors are the same, and I'll put the input over here, let's call that V1, and we'll call the output V3, and I'm using that notation so I could call the node here V2. Now I have a feedback loop going from the output of the OTA here to the negative terminal. And I similarly have another negative feedback loop here. If these are operating in the linear region, again, I'll talk about that detail later, we could say that these OTAs are basically modeling resistors. But assuming that the OTAs are ideal, they have infinite input impedance, so they're not drawing any current. So if I wanted to draw an RC version of the circuit, I would need to put some sort of voltage buffer here. So it would look a little something like that. Now, this should look familiar. This is basically two one-pole passive filters that are buffered, and this isn't very interesting. So to make it interesting, we're going to add a third OTA that's going to give it some feedback. So let me scroll up to make some room for that. Okay, so I'm going to draw my feedback OTA up here. I'm going to denote this with the transconductance gain of GM3. I'm going to take the output V3 and feed that to the negative input of this OTA. And interestingly, the feedback from this OTA is going to go to its positive input. That is not a mistake. And the output here is going to feed this node here. So let me write down a Kirchhoff's current law equation for this node here at V2. I'll say that there's a current flowing out of GM1, and that's going to be equal to V1, the positive voltage input here, minus V2, which is going into the negative input, times the transconductance gain GM1. Notice I'm using GM1 to both refer to the OTA itself and its transconductance. And let's see, I'll also have a current coming out of GM3 into this node. So that's going to be V2, which is going into the positive terminal, minus V3, which is going into the negative terminal, times the transconductance gain. Oh, I'm not being consistent of where I write things. Oh well. Anyway, I'll have a current flowing down here through the capacitor, and that's going to be equal to, let's see, it's going to be equal to V2 minus 0. So I'll just write V2. And then by Ohm's law, we need to divide by the impedance. The impedance is 1 over CS, so I'll just multiply by CS. All right, so what about this node up here? Well, let's see. I have a current flowing out of GM2, and that's going to be equal to V2, which is going to the positive terminal, minus V3, which is going to the negative terminal, and that's all times GM2. And then I'll have a current flowing down through this capacitor, and that current flowing down through the capacitor is going to be equal to V3 times CS. All right. Again, notice that I'm assuming that no current is flowing into the inputs of the OTAs. That's an assumption. That's not really totally valid for BJT input OTAs, but it's pretty good for MOSFET input OTAs. Okay, so I want to play with this equation on the bottom here a little bit. I want to get an expression for V3, the output, in terms of V1, the input. So for that, I need to get rid of V2. So multiplying through by GM2, I have GM2 times V2 minus GM2 times V3 equal V3CS. Let's see. So I can have GM2 V2 on the left-hand side, and I'll have V3 on the right-hand side. So I'm taking this term and moving it over to the right-hand side, so the minus becomes a plus. I can pull out the V3, and I wind up with CS, which was here originally on the right, plus GM2. So let's see. V2 is going to be equal to V3 C over GM2S dividing through by GM2. And then at the end here, after I divide by GM2, I just have 1. Okay, so let me rearrange the first expression that we created for the node at V2. All right, GM1 V1. And let me move everything else over to the other side. So I'll write GM2 times V3, and then let me put all of the other V2 stuff on the right-hand side. So I'll write this as plus V2. All right, so I have GM1 with a minus. Move that over to the other side. It becomes a plus GM1. And then I'll have a GM2. When that moves over to the other side, that becomes GM2. And then I have CS originally, so I'll add CS here. All right, so now I need to take this expression for V2 and plug it in here. So let's see, that's going to give me GM1 V1 equals GM2 V3. And actually, let me write this going the other direction. So let me write GM1 minus GM2 plus CS multiplied by, let me write this as C over GM2 times S plus 1 times V3, just so that the voltages are all on the right. I think that looks better. And shoot, I made an error here. Let's see. This term here, I have the V2 minus V3. This is GM3. That's what goes here. So let's see, that term wound up here. So this should be GM3, and this should be GM3. And we have some more repairing to do because I also have this V2 times GM3. Where did that go? It went here. So I need to make this GM2 into a GM3, and then this GM2 becomes a GM3. Okay, now we're ready to slog through some algebra. See, if I was a more dedicated YouTube educator, I would go back and redo that whole section, but I'm not that dedicated. So anyway, let's see. GMV1 is equal to GMV3. Okay, I'll multiply all this junk by C over GM2S, and then I'll multiply all the junk by the 1. Okay, so I have GM1 minus GM3 all over GM2, let's see, times CS, and then I'll have c squared s squared over GM2. And then I'll have this whole mess times 1. So I have GM1 minus GM3 plus CS times V3. Whoops, I forgot a 3. Okay, I'll have a GM3 V3 term here, a GM3 V3 term here. So these terms cancel. And let's see, I want V3, so I'm swapping sides here, is equal to GM V1 divided by this whole mess. Divided by this whole mess. Oh, wait, what is the subscript here? This should be a 1, this should be a 1, this should be a 1. In case you're wondering, no, I didn't really plan this out. All right, so I have c squared over GM2 plus, s squared, plus, let's see, we'll write this as c times 1 from here, plus GM1 minus GM3 all over GM2 times S, and then plus GM1. So let me write V3 is equal to V1, and I'll divide everything in the numerator and the denominator by GM1 just to get a sense of what's going on. So I'll write 1 over c squared over GM1 GM2 s squared plus, let's see, I'll write this as c over GM1 times 1 plus GM1 minus GM3 over GM2 s plus 1. So this is sort of the form that you generally see with time constants. Let me scroll down. Okay, so this clearly has the form of a second order low-pass filter, and you could figure out the natural frequency and the Q and all of that. So to make that a little smoother, I'm going to assume that GM1 is equal to GM2. And you can work this out without this assumption, but I found that having these be separate doesn't really give you any interesting circuit design possibilities, at least as far as I can tell. So we might as well do that. All right, so we would have V3 is equal to V1, 1 over c squared. Actually, let me write this as c over GM squared, and this is GM1, s squared. And then I'll write this as c over GM1. And let's see, if GM1 equals GM2, I'll have a GM1 over GM1, which will give me a 2. And then I'll have minus GM3 over GM2. And actually, to handle this, let me factor out a 2. So what I'm going to do is I'm going to erase the 2 here. I'm going to write a 2 in front, and then I'll write a 1 here, and then I'll put a 2 in the denominator to make that all work out. All right, so then I'll have S, and then I'll have plus 1. Okay, to get this into my canonical form, where the S squared is by itself in the denominator with the coefficient of 1, let me divide the numerator and the denominator by the c over GM1 squared. All right, so I'll write V3 is equal to V1, and then up here I'll have GM1 over c squared. Then I'll have s squared here. And then, let's see, I'll have GM1 over c times 2 down here, 1 minus GM3 over 2 GM2. If you've stuck around this far, thank you so much. I know this is not the world's most exciting thing. And then I'll have GM1 over c squared. All right, So this is now in my usual canonical form. And that canonical form is usually something like h of s is equal to omega n squared over s squared plus omega n over q s plus omega n squared. A lot of people will write this in terms of time constants, tau instead. I like to think about natural frequencies. Your mileage may vary. You can flip between one and the other. Anyway, I see here that my omega n squared corresponds with this term here. So I now know that omega n is equal to gm1 over c. That's my natural frequency. And let's see, my omega n here in this middle term, that matches here. So then the rest of this here must be 1 over q. So I could write q is equal to 1 over 2, 1 minus gm3 over 2 gm2 like that. Actually, why did I write gm2 here? I could have just made that into gm1. Anyway, I'm assuming that gm1 and gm2 are the same. So to make this more clear, let me make this a 1, and let me make this here a 1. All right, that makes it clear that I made gm1 and gm2 the same. So I've never seen this used in a music synthesizer because I don't have independent control over Q and omega n. If I change gm1 in order to change omega n, then I'm also changing the Q. So generally in synthesizers, we use things like state variable filters and solid key filter structures that allow independent control over Q and omega n easily. Now, there's probably a way to rig this all up, but you would need to change gm3 while you're changing gm1 in order to maintain the same Q, and that's probably complicated. Now, where I think this might be interesting is in building fixed filter bank kind of filters for musical applications. Remember earlier I mentioned we've assumed that the OTAs were operating in the linear region. If you push an OTA, it has this really nice hyperbolic tangent nonlinearity, both for BJT-based OTAs like the 3080 and the 13700, and MOSFET-based OTAs if those OTAs are operating in the subthreshold, aka weak inversion region. And even in strong inversion, the above threshold region that you're probably more used to where your MOSFETs have a square law, the overall behavior is qualitatively similar. You have a really nice saturating nonlinearity. So you might build a filter like this even if you keep GM1, GM2, and GM3 fixed just to get those nice saturation properties. I think that might be interesting. Now, people who use this kind of filter are generally building fixed filters on a chip. And on a chip, resistors are kind of a hot mess, and it's often convenient to try to replace resistors with OTAs, or I should just say use OTAs or transistors in general instead of using resistors. And so they like structures like this. Anyway, I learned about this from my colleague Jennifer Hassler, and I thought it was interesting and just wanted to share. Oh, there is something else I wanted to talk about, which is how we might adapt this for a PCB level design. What you see here is typically how they would put it on an integrated circuit. So we usually don't like to take the feedback to an OTA input directly from the output of the OTA when doing PCB level design. We like to put in voltage buffers here. If you have a good understanding of why people typically do that, please leave a comment below because I don't really understand it that well myself. Anyway, let's see. We'll take the output from a buffer here and make that be our V3. And we'll also put a voltage buffer here. This could be something like a operational amplifier with just the output strapped to the negative input, or it could be something like a source follower made from a JFET, or maybe you have something like in the 13700 chip where you have a Darlington buffer configuration. Anyway, let's see. So we'll take the output like this, and here's my V2. And the other thing we want to do that we can't really do on the chip if we're avoiding resistors anyway, is we might put in some resistor dividers in order to keep the overall, in order to help the OTAs operate in more of a linear region. So let's see, I might take V1 and run that through a resistor divider. And when you ever see me write a divider like this here, this is something like R big over R small. We want a lot of attenuation. So let's see, I'll have R big here, and I won't bother writing the R big and R small. I'll assume you can figure that out. Let's see, and I'll have a resistor going to ground here. Let's see, this is getting a little crowded, but hopefully you get the idea. I'll want a resistor divider here. So I have R big and an R small going into that terminal. Let's see. This is getting to be a bit of a mess. I probably should have just redrawn the whole thing with more room. Oh, this is ugly. Okay. There's a resistor divider. Let's put a resistor divider here. So I'll have resistor divider here. And we want one going back this direction. So let's make this some resistance R big, and then I'll have some resistor here. So in your head, redraw this so that it's less disgusting looking. If you set all of your R bigs to be the same and all of your R smalls to be the same, then essentially you can take whatever attenuation you're getting from the resistor divider and just fold that into your formulas. You can just fold that into the transconductance gain. Anyway, if I were to build this on a PCB, this is probably how I would start approaching it. Oh, hi, it's me again. I'm not done yet. I thought I was. I was sitting here at the editing stage thinking, oh, this is kind of nice. I'm almost done. And then I realized I made another mistake. So I don't want to take the voltage output from this node. I want to take it from the output of the voltage buffer. And if I do that, then these two OTAs here can actually share a divide down ladder. So I could put R big here, and I could put R small here, and that attenuated voltage can feed both of these. So it can feed here, and it can feed here. And let's see, I should probably also put a buffer here in the feedback loop here. Okay, I think I like that.